All right, let's begin, shall we? All right, maybe I'll give it a couple more minutes then to see if the YouTube one fires up. Looks like good to go. Today we are talking about functions, which is by far my favorite topic, which is crazy to say because I love all the topics, but functions is my favorite. And it's my favorite because I'm a functional programmer, which is that's not something many of you know anything about, and that's fine. You'll learn about that further down the track. If we're looking at the textbook, functional programming kicks in down here when we get to the programming languages topic and the provably correct programs topic. We start to touch on it a bit more with the practice of programming topic as well. But broadly, there are two types of computer programs: imperative programs and functional programs. And by far the dominant one in industry is imperative programs, but by far the best one is functional programs. And I fell in love with functional programming, and so I'm a functional programmer. I don't spend much of my time actually using functional programming languages, though. I spend all my time in imperative languages, but I still think like a functional programmer. So that's for you to learn more about further down the track. But let me try and give you some of the computer science background to this, because I think that's very instructive. At this point, and I've probably said this before, but I'll say it again in case I haven't, by the time we got to the end of topic 6, conditions, and in fact, just with topic 4 and topic 5, variables and conditions, we actually had everything we needed to program. A couple of people who I got up some pictures of. This guy, okay, maybe not that guy, but the guy that guy played in a movie, and this guy, and this guy, are the 3 people responsible for, well, not the 3, but the 3 main people responsible for the computers we have in front of us right now, the one I'm using for streaming this. We'll start off with the first one, which was this guy. Whoa, look at that data image. Alonzo Church. So in the, I always get my times wrong, and since I'm streaming now, I should probably double check all these and get the dates right, but 20s, 30s, early 20th century, mathematicians had a question they were asking themselves, which is, can I build a machine that does maths so that humans don't have to do it anymore? Because if you get deeply involved in maths, it's quite a mechanical process. You're proving things using existing knowledge and logic. And the game in maths is to search the logic space and come up with the magic combination of existing theories and logical process that gets you from your theory at the top to your proof at the bottom. And I started to think about whether that could be automated. Well, they'd probably been thinking about it for a while, but it became, I guess, the big question. And so these things get phrased in their mathematical way, and someone, the name's already gone, which is crazy because I know it, but someone posited the problem of, can you write a machine, or would they use the word algorithm? Can you write an algorithm that can work out the trueness or falseness of any mathematical statement? So if I give you the statement 1 equals 1, that's a true statement. If I give you the statement 1 equals 2, that's a false statement. Can I write an algorithm that could work out the truth or falseness of a statement? And that started off a whole field of research. And the first guy to have a good solid answer to that was Alonzo Church here. And what he did was he created a whole new style of maths, which he called the lambda calculus, that encoded algorithms. And remember, there weren't computers at this stage. That encoded what an algorithm was, and then he proved that no, you couldn't write an algorithm that could answer all those questions, which was a bit of a bummer, I guess. But on the other side, it also showed you the breadth of things you can do with those algorithms, and it was almost everything. There was only a very small amount of stuff that you couldn't do. So one of his students was Alan Turing, and this is not Alan Turing, this is an actor playing Alan Turing, but you've got to mix things up. And he took on, amongst other things, the same problem, but from the opposite angle. Alonzo Church's lambda calculus was unbuildable. It was a piece of mathematics, not a piece of machinery. But Alan Turing solved the same problem with something that was a piece of machinery. It was a logical piece of machinery called the Turing machine. And it had a head that went back and forth on a tape. He didn't build it, he just described it. went back and forth on a piece of tape. You couldn't build it because it had infinitely long tape, for one thing. And he described how that was exactly the same as Alonzo Church's lambda calculus, and so it had that it had the exact same properties. The super cool thing about that is that it was buildable. So as soon as Alan Turing had done that, you realized, well, not only do I have this machine that can answer, okay, it can't answer every question, but it can answer almost every question, and there's a concept that I could build it. Later on came von Neumann, who helped us with the stored program part, which is absolutely vital to the computers we have now. And off we go. Von Neumann machines were slightly modified Turing machines, and then every computer we have now is still a von Neumann machine. So that was the 50s, I think, when Neumann was doing that work. I think he might have been involved with the, all those scientists after the Second World War in America. So what's that got to do with functions? Well, what it's got to do with functions is that the lambda calculus here, these turned into programming. The Turing machine turned into a computer, so the languages in which it was written turned into programming languages. And the language it was written in was just the language of variables and conditions. All it had inside it was variables and conditions. And so he had proven that just with variables and conditions, you can calculate anything that you can ever possibly think of calculating, and there's a few things you can't. But they turn out to be at the edges, and we can still do a lot of great things with our computers anyway. Cool. And that's why variables and conditions is enough to do everything. It's an extremely awkward way to do everything, but you can. And because it's so awkward, we build structures on top of those that work better for us. Loops, which were a bit like a condition but different, and so on and so forth. So that you should think of variables and conditions as kind of like the core of programming from which everything can build. And even the very simple language with just those things would probably let you do everything in a very awkward, unpleasant way. Okay, so the Church's work, which had come before, remember, actually only had variables and functions, nothing else. And in fact, a restricted version of variables where you can't change the value inside them. And remember, it was equivalent to Turing's work, so it could also do absolutely everything. So even before computer science came around, even before computers invented, we already knew, thanks to these two, that either combining variables with conditions or combining variables with functions is enough to do everything that computers can do. And I think that's super cool. And it turns out if you take the combining variables with conditions loop approach, you're on the imperative programming side, which is what most of our languages are. It's what processing is. It's what Java is. It's what C and C++ are. It's what Python is, so on and so forth. And if you take the variables and functions path and build a programming language down that path, you're a functional programmer. And those are languages like ML and Haskell and what other languages have we heard of? There's not a lot of function. Oh, Lisp. Now you might not have heard of those because they're not used in industry a lot. But that's perhaps, maybe not so much an accident of history, but something that's changing. More and more functional features are coming into existing programming languages. So it's becoming more and more important. No, I don't think so. Let me just fiddle something. So the mic's sounding a bit funny. One thing could be the zip on this jumper getting in the way. Let's just get that out of the way and see if it makes a difference. I've been trying to get my better mic, but not allowed out the house. I'm stuck with this thing that came free with some old phone. Okay, so it's probably the zipper then. Okay, thank you. Right, so that's the computer science background. And why am I telling you that? Well, I'm telling you that because we're getting, first of all, it's interesting, and we're doing a degree where we're setting you up for computer science, not just for programming, but also because we're getting to the point where there's more than one way of doing things. Before, if you just got variables and just got conditions, then there's only one way to, well, not only one way, but there's a limited number of ways to do everything. And as you start building in more and more of these features in the programming languages, you're often finding infinitely many ways to write the program. So I wanted to give you an idea of why that is. And for you, it doesn't really matter which path you go down. You choose the path that works best for you. So we're also going to be talking about, in a world where we have variables, conditions, and loops, and a bunch of other things, some of which overlap, how do we choose which ones we use? What's the reason for having functions in that environment? The main reason for having functions in that environment is code organization. It's just incredibly useful for code organization. So all the programming languages combine bits from the church path and bits from the Turing path, because the flip sides of a coin, there's very few things in life where if you've got two sides of a coin, you only ever pay attention to one side. All right, with that background out the way, let's think about how functions actually maybe work. Well, what a function is. So I've got a key point up here that says a function is a named piece of code that can be supplied with some inputs and return a value back to the caller. And that should sound very familiar, because that's what an algorithm is. And that's not a coincidence. We have this algorithms topic in here specifically to set you up for functions. Very much of what we spoke about here in algorithms is true of functions, but we took it away from the specifics of functions in processing and just talked about it in a general sense. That's why I've been bouncing back and forth with names like algorithm and function for things like draw and setup, because they're both. We have built into processing a whole pile of functions that we've been using all the way along. And the easiest way to get started, I think, is just to think about or look at those functions. And keep this in mind. It's a named piece of code supplied with some inputs, maybe, and return a value back to the caller, maybe. And we got a couple of keywords to pick up in there. What's a caller? What are parameters? And we'll get through those. So each of the videos from Schiffman here, so he's got the basics, he's got the modularity, which is part of code organization, and the usability, which is part of code sharing. Okay, so the built-in functions, let's look. With the reference, almost everything in here is a built-in function. If it's got parentheses after it, it's a built-in function. We might have called those algorithms before. And we're breaking up between built-in variables and built-in functions. If it doesn't have a parentheses after it, it's a built-in variable. If it does, it's a built-in function. Those heaps we already used, right? Circle, line, ellipse, these are all functions. But let's think of them in terms of that definition I gave before. It's a named piece of code that can take in inputs and may return something. So this is the name of the piece of code. These are the inputs the piece of code takes. And sometimes it returns something. Line doesn't return anything. It draws something on the screen instead. But name, inputs, maybe return. This shouldn't be unfamiliar, because this should be all the kind of stuff we've been doing from the start. We just didn't want to start off, you just can't start off a course with functions, even though you're using them from day dot. So we use the language of algorithms instead. Or built-in operations was the other thing we called them. So let's look at a function that does return something. They're down here with the maths functions mostly. Absolute value. So an absolute value is a named piece of code. There's the name, ABS. It takes an input. There's the input, N, and it gives something back, which is the absolute value of the number you gave it. So it's got a return. No magic. Nice and easy. But we're going to start to bring in the proper language of functions now. Let's just start off by writing a simple program, as always, that uses some functions and defines some functions, and I'll start talking around that. One of the core things to understand about functions is exactly the same as we had with variables. They have a definition that happens once, and they have uses which happen many times. Oops, I'm going into Java mode. Soon I'll be starting up teaching a course on Java, and you're going to find me slipping into Java void setup. Better than last year where I was teaching Java processing and Haskell all at once and I kept slipping between the two. Okay, so as always, I'm on my big screen, and background. Okay, so it's my standard starting point. Processing's got to warm up today. There we go. I just wanted to point out in here, using that language I used before, what we've got in front of us. These are all built-in functions. Size is a built-in function, background is a built-in function, no stroke is a built-in function, fill and ellipse, all built-in functions. The name of this function is size, its inputs are 800 and 800, and it has no outputs. The name of this function is background, it has a single input which is 0 and has no outputs. Stroke is the name of this function, it has 0 inputs. Fill is the name of this function with 1 input, again no outputs. And ellipse is the name of this function which has 1, 2, 3, 4 inputs. And again, no outputs. These are all function uses. Let me get a variable in here so that I can compare with variables too. All right, what am I going to do with xpos? I'm going to make one of these. I like these kinds of programs. Int ypos, and they'll start off at well, they'll start off wherever, but we'll start at 0. And what I'm going to do is I'm going to write one of these programs. I like these programs that kind of follow the mouse around but slowly. And the way I do that is, let me just give you an example. When I load this program up, I'm not using xpos and ypos yet, so let's use them. So no questions, I'm assuming. Please pipe up. I prefer questions than no questions, but you know, maybe there's nothing to ask questions about. It's xpos and ypos over there. Imagine when the mouse is down here, which is at 800 by 800. If I want to make an animation where this kind of springs towards the mouse, the way I would do it is I would do a maths calculation that took the current x position and maybe went halfway towards the mouse position, because that would make it move fast when it's a long way away and then slower as it gets closer. So I work out the distance between where I'm pointing at my screen, but you can't see that, where I currently am, xpos, ypos, and where I want to be, which is mouse x, mouse y. I get the half of the distance and I adjust my position according to that. So that's what I'm about to do. So let's do that. Int new xpos equals mouse x, which is a global variable I can always use, minus xpos. What I'm going to do is I'm going to get half the distance between the two and add that to the current xpos. And so that will move me halfway closer, I think. And I'll do the same for y. And so now I won't use xpos and ypos in here. I'll use, so I don't need the new xpos. I just want to update xpos and ypos directly because I want them to be ready for the next time around. Let's see if that does what I want. It's moving very fast. It's very hard to tell from the version that just follows with a little bit of lag. So let's change that from a divide 2 to a divide 8, which should slow it down a bit. There we go. Quickly and then slowly. And I want to go to an even lower number because the frame rate at 60 frames a second is getting there quite quick. So it's like we have it on a spring. It's slowly following after, it's following after us quickly and then slower. I like that program. What was the point of that? Well, the point of that was to bring in some variables just so I can talk about the things we already know about variables and compare that to what we know. We're going to learn about functions. This is a declaration, and it's important we understood the difference between declaration and use, remember? I've got two declarations, but there's only one for each variable. There's a single declaration for xpos, a single declaration for ypos, and then here, use. And here are 1, 2, 3 uses all in one line. And same down here. And then we got uses on this line as well, of each, xpos and ypos. And so you remember that the declaration of a variable set up a slot in memory, and the use of a variable went and looked in that slot to see what was in there. That's the mechanics of what we learned about variables. Well, now we're going to learn what the mechanics are for the two different phases of functions as well. What we have on the screen here is a use of a function, and a use of a function, and a use of a function, and a use of a function. And I know I'm being monotonous, but sometimes that's how we've got to go when we learn things. And a use of a function. There's no function uses on line 14 or 15 though. Okay, so what happens when we use a function? That's the first thing to ask about. We're not even going to worry about declarations now, we're just going to worry about use. Well, deep inside processing somewhere are some code to go with each of these functions. The code probably looks something like, I'm just going to do background. I'm getting ahead because I'm showing you some more stuff, but let's just do the grayscale one, right? There's a chunk of code, and background, you actually know what background does. It's been doing it all along. It's a little bit more than this, but logically, it actually just goes 0, 0 with height. It sets goes no stroke and fill grayscale. Okay, so that's actually, don't worry about understanding that, but that's actually something approaching the code of background. What I want to show you is that that function is 3 lines of code. A function is a chunk of code, always a chunk of code. And in this case, it's these 3 lines of code. So the function call, remember that a variable use requires going off and looking in that slot of memory and getting back whatever's inside. A function use requires going off and looking at that block of code and running it top to bottom. And that's all. Easy. So it's really quite a lot like a variable. A variable's got a value inside it, and so when you use the variable, you find out the value that was inside it. A function's got code inside it, so when you use that function, the code gets executed. Easy. That's what's been happening the whole time. Every one of these built-in functions, somewhere deep in processing where we can't see it and we don't need to see it, there's a chunk of code that's getting run for us. We probably can't understand how that code works. And if you're smart, you realize that there is actually something more going on in here in the background, because if this was the code, then now we kill our stroke and our grayscales for all of other shapes, which doesn't happen. All right, so that's use. Well, where's the equivalent declaration for a function? Right here, we've got 3 of them, believe it or not. Let's leave that one out of it for now. But we already have the equivalent declaration for a function, just like variables happens once and once only. And the syntax for it is this syntax and this syntax. These are both function declarations. So we've been practicing them the whole time without realizing it. And the sequence for them is there's a return type. We'll talk about that in a minute. There's a return type, a name, some parameters, a curly brace, and a curly brace. And inside is a chunk of code. And that's why we might have been slipping into language like calling the draw function or calling the setup function or using the draw function or using the setup function. Because executing their code top to bottom is exactly what calling the function, using the function does. So calling is the specific name we use for the use of a function as opposed to the declaration. So just all you got to remember: return type, name, parameters, curly brace, code. But so that's the setup one. There's the draw one following the same pattern: return type, name, parentheses, curly brace, code, curly brace. And the background one I wrote or made up does the same thing: return type, name, parameters, curly brace, code, curly brace. But here you can see the parameters is something very slightly different. Well, no, not very slightly. It's different. The two we've been writing the whole time had no parameters, no input values. So they just had empty parentheses, which is what we do for no input values. Background required an input value, so we had to put that inside the parentheses, and it's exactly where all the input values go. When you have a function like ellipse that's maybe got 4, then you do the exact same thing. You don't actually know what goes in here. And you put commas between each one in the declaration, just like you put commas between each one in the use. So you'll notice that the use and the declaration line up in this part. Ellipse, the name, parentheses, then each of the inputs, the name, parentheses, then each of the inputs. The thing that's missing from the function call is you don't worry about the return type, and you don't worry about the code inside, obviously. You wouldn't be repeating that code every time. The whole point is to call that code for you automatically. So the way these inputs work is interesting now. I've shown you an example in the background of the way the inputs work. But I want to step back a bit and just refresh what we're talking about here. Make sure we're on solid ground before we move forward. So we've covered that functions are chunks of code. We've covered that they have declarations, which we're just learning the syntax of now. They've got uses, also called function calls, which we've been practicing the whole time. We know the syntax for that. And we have parameters, inputs. Functions take inputs and maybe return values. All right, was there a question? Okay, so the question, which I think come on the comment, is this is a function that I was able to break down into smaller functions. Are there functions you can't break down into any smaller functions? They would be called primitive operations. And the primitive operations depend entirely on the system you're programming. So if you were programming, remember processing is a version of Java. If you're programming Java, there are a pile of primitive operations which are defined inside the virtual machine. And there are tens of thousands of them. That's what's cool about that virtual machine. And so you use any of those, and you couldn't break those down any further if you tried. But you can build up bigger functions on top of them, which is great. If you're programming in C, for example, the set of primitive operations that you can't break down are the things in the C library, which are very reasonably large and useful, but very, very much smaller than the ones in Java, maybe 2 factors of 10 smaller. If you're programming in assembler code, then the only primitive operations you have are the primitive operations defined on your CPU, which is the loads and stores and adds and multiplies and divides. So it really depends on the environment in which you're programming as to what your primitive operations are. Now, when we're in processing, our primitive operations are exactly background, no stroke, fill, these things that are in the reference library. The fact that I can pretend and guess what it looks like inside that's not really what you ever do. So those are, and that's why we call them primitive operations at the start, because we don't break them down. We tend to build them up. Ellipse is a great example, right? I can't break that down. I can't tell you smaller things in processing I might be able to put in there, because putting an ellipse on the frame buffer is actually go and find the point on the frame buffer, which requires the operating system's help. All right, so an important part of, if you just had chunks of code that we could call, which we do with setup and draw, right? They're just a chunk of code, they go from top to bottom. They're just a chunk of code, they go from top to bottom. That would be good and that would be useful. And there are a lot of functions that work like that don't take in any input, they just do stuff. No, I shouldn't say there's a lot. There are some functions that work like that. They don't take in any input, they just do stuff. But there are way more functions that do have to take in input to do a reasonable job. There would be no way for me to write an ellipse function that didn't take in any input, right? If ellipse worked like draw and setup, it would just be draw me an ellipse. And, well, where does it go? How wide is it? Ellipse would just be doing the same ellipse over and over and over and over again. That only really works for a few built-in things like setup and draw. It's okay for draw just to do the same thing over and over again. We've got all these features to look up globals and things to find out how to draw each time. But most functions need some input to tell them how they're going to run. And what's really happening is that you don't want the exact same piece of code to run every time. You want almost the exact same piece of code to run every time. Background's a great example. You want something like these 3 lines to run every time, but not exactly the same. On one of the runs, you want it to fill with a 0 in the background. Another one you want to fill with the white in the background. Another one you want to fill with green in the background. And so you need to pass that information in. So the same piece of code, which is those 3 lines, 2, 3, and 4, can act differently depending on what information you've given it. We already know how to make a piece of code act differently based on information. And that's variables. If the code is running and using some variable that's in the memory, then depending on what's in that variable slot will depend exactly how it runs. Correct? Correct. We did that exactly over here. We wanted to draw an ellipse on the screen. So draw is just the same 5 lines of code running over and over again. Exactly the same 5 lines over and over again. But on every single frame, it's showing me something different. And the way it's showing me something different is because there's a variable somewhere in the memory that's being used to, that's being looked up, and that variable is changing on every frame. So the same piece of code is doing something different on every frame. We do the exact same thing with functions. What we say is this function should not run the exact same every time. It should run almost the exact same, but one part of it should change every time. And that part of it I'm going to stick in a variable and make sure that variable is in memory, and it'll use that variable to do its job. And that's what these 3 lines are doing. On line 3, it uses a variable called grayscale to do its job. The difference with functions is that instead of the variables just appearing magically, the variables appear in the parameter list. The secret to making functions work is that not only do they have a name, but they have a kind of private set of variable declarations just for them. Just like I had a set of variable declarations up the top here for xpos and ypos, they were globals, they were available for everybody. Down here, I've got another declaration that's secret and private, only available to the background function. But that's the piece of information it needs to have varying so that it can do different things every time it's called. Because remember, one declaration, many calls. Just like with variables, one declaration, many uses. So this thing here in the parentheses, we call it a parameter list, and it's the input list. But syntactically, it's a list of declarations, variable declarations. Just like lines 1 and 2 here are variable xpos and ypos declaration. In line 7 here, we've got 4 variable declarations. int x, int y, int w, and int h. And they're exactly the same. Logically, I'll go back to the background one. Logically, you can think of them as acting like this. Whoa, you can think of this declaration in here as kind of setting up a new variable that's ready to go. We'll talk next week about exactly what we mean by kind of. Okay, cool. Cool. But here's something I can't do that I'm used to doing with variable declarations. Over here on my variable declaration, I was able to put an equals 0 up here if I wanted, right? I could double up and do a declaration and an assignment in one hit. And I wanted to do that. I would want to do that because not declaring variables is a bad idea. What values goes in them? Well, the only value that could go in that one would be 0. If I wanted to start it off at 10 or something, I'd have to do that myself. Well, maybe since this one's a declaration, maybe we can do the same thing. Let's see. And we've got a squiggly underline because we can't. We can't declare and initialize up here because that would defeat the purpose of functions, and I'll tell you why. The secret, another secret to functions is that the call for the function over here sends in the starting value of the variable. So because I've got a background of 0, when I call the function, it's like executing lines 2, 3, and 4 as if I set grayscale to 0. And if I did background 100, it would be executing lines 2, 3, and 4 as if I'd set grayscale to 100, even though I haven't. So in reality, the way function calls and function definitions interact with each other is that the function definition defines those 3 lines of code, or however many lines of code, that are going to run when the function's called. It defines which variables it needs to know so that it can run. And then the variable use will fill in initial values for each of those variables. So on background, because there's one variable we declared that the function needs, there's one value we pass in for the initial value of that variable. On ellipse, because there are 4 values that it needs to do its job, there are 4 values we have to pass in as the initial version of that. So more precisely, the call to function ellipse with xpos, ypos, 80, 80 is the same as executing the body of ellipse with x equals xpos, y equals ypos, w equals 80, h equals 80. So we kind of send those values over and they slot into the slots left behind by the x, y, w, and h. And then when the body runs, it does whatever it needs to with those. So let's build us a function that we might use. So I put this in a separate sketch over here because these aren't real functions. I just made them up to demonstrate some syntax, right? Let's write a real function that's useful for us. Although now's a good time to stop to see if anyone's got any questions to ask and to give you a chance just to ponder while I have a bit of tea. It's just gone cold by now. I need to get a better mug if I'm going to keep tea for now. So I'm going to write my own function now, one that's useful for this program. The function I'm going to write is one to do this little bit of maths here. It's not very hard, but you know, this was the maths for get a bit closer. Get a bit closer from this position to this position. So I'm going to write a function to do that. Now, functions always have return type, name, params, curly brace, body, curly brace. That's what they are. And I've just got to work out what each of those things is going to be. And this here, lines 19 to 21, that's a function declaration. Now it's complaining because those aren't proper things to put in there. Now, params is what information does this function need to do its job? Well, name is a good start. A name is what's this function doing? And I said get a bit closer. That's reasonable. What information does it need to do its job? It needs to know the position it's starting at and the position it's moving towards. So it needs two different integers, the integer it's going from and the integer it's going towards. Yep. And those get set up as declarations. So I have to use the declaration syntax, int from, int towards. It gives back a value, actually. It gives back the new value of my position, you know, the position that's taken me a little bit from there towards there. So a function that returns a value, you have to work out what type it's going to return. If this one's taking in integers from an integer towards and giving back a new integer, that's the new position, then my return type is integer. So I just have to tell it what type is going to get returned, not exactly what value yet, that comes later. And then the body just has to do the work. It has to be the lines of code, right? Well, in this case, the lines of code are, there's only one line of code, right? It goes 2 minus from divided by 24 plus from. That's the little calculation to get me what I want. Whoops, that's towards. Towards minus from divided by 24 to plus from. But that's not a full expression yet. So that's not a full statement yet. That's just an expression. I need to put that into a variable maybe to return it. Okay, so the next thing it's complaining about is that this doesn't return anything. As soon as you put an actual return type in, because your function is going to give back some information, then you have to have a special line at the bottom using the keyword return that just tells it exactly which value to return. If I write return 7, this function, no matter what I give it, will always give back 7, which is not useful, but that's valid syntax. Really what I want to do is return back the value I calculated here. So this guy takes in two numbers, from and towards, does a little calculation to work out a new value that's about 1/24th closer to the towards value than the original one, puts that in a variable called ret and returns the value in that ret. So I can now use that function over here to do the same as what the code was doing before. Just going to run this to see if it is doing the same as before. Yep. It's found my, I changed my background to 100, but otherwise we're working fine. Yeah, so there's a question there about whether subroutine, what the word subroutine versus function means. There's lots of names to think about here, so let's just go through them precisely. We said algorithm early on for, you know, any solution, any recipe for a thing. Then we use the word code to mean an algorithm that you're actually writing in a program. Then I started talking about chunks of code and calling them functions. That's fine. There are lots of other words for functions from the histories of computer programming. Words that will come up will be method, which has a more precise meaning, but in our environment doesn't matter. Procedure, which can have a more precise meaning, but really means function. Routine or subroutine are both phrases that mean also function. Lambdas, closures, all of these really are just functions. Some of them have some slightly different characteristics that we might care about at some other time, but when we're learning at this level, if we see any of those, if we see algorithm, code chunk, the procedure, subfunction, function, lambda, closure. Can I think of any others? Then we just think of a function. We're going to consistently use the word function here, though. That's definitely the best one. If you're interested, you can ask me offline what are the environments which you might use those other ones. Okay, so we have now our own function declaration, and it uses this syntax that we know we need, a type, a name, two different parameters coming in, and one return value. Sometimes you'll see people call this a return parameter, but it's better to call it the return value, I think. And then we've got two uses of this function. One use here, which is the function calls, and one use here, function call here. And notice that we pass in the exact right number of variables to match up. And the other thing that's important about passing in those variables is that they're both integers. This one's told us from must be an integer, towards must be an integer. So if I try and put in a character here, it will helpfully complain. Characters it won't complain because it can turn them into integers. That's annoying. If I put a boolean in here, it can turn those into, no, it complains, finally. So when I tried to send a boolean in, as just like you couldn't write int from equals true, you can't declare it as int from and then in the function call set it to true. Okay. So we've got demonstrations of everything now, quite small and neat definitions, I think. Next, let's actually trace the flow of this code, because the fact that calling a function means going off and running its code from top to bottom means that it does break up the flow of the program, similar to how conditions and loops broke up the flow. It doesn't just go top to bottom anymore. What's the flow of this program? Well, we're going to assume that all these built-ins just happen magically. We're not going to try and chase the flow inside those. But we are going to try and follow the flow of our own function. And I'm going to use the debugger to help me because I think it's quite useful in this case. Just going to get rid of the extra stuff that might not apply anymore as we start to change the program. Another thing to notice, is that my function declaration had to be back here at the top level. I couldn't do this function declaration inside the draw, and I couldn't do it inside the setup. It's got to just be done in its own space. Notice also that what we really have here when we do the syntax is we're declaring our own setup function and we're declaring our own draw function and never using them. We're doing the single declaration step. Processing is actually doing the use for us in the background. Processing is going, I'm going to use the setup function for just once, and I'm going to use the draw function many, many times over and over according to the scheme that I've set up. All right, let's get the debugger on and let's follow this flow, see if it does what I hope it will do. It's always a mystery to find out if the debugger does what you think. We're going to learn about a new type of step here as well in a second. So just got to get my shortcut on it. Step into is Mac Shift J. Okay, so I'm going to start running this program, and I put a breakpoint there on line 12, which didn't do anything. Why is that? Try breakpoint down there. Okay, that worked. So I put a breakpoint on line 11, which is working. Now, let's check the debugger. What does it tell me? Well, it tells me that I'm executing line 11 right now, and it tells me that there are two variables that have been declared, xpods and ypods, because remember, as soon as you declare a variable, it appears over here in the debugger, and there's a slot in memory for it. And then it's got all the built-in processing variables too, which are useful. And luckily there's a couple that I'm going to use, width and height and mouse X and mouse Y. Now I'll step. Whoops. Step. So when I asked the program to take the next step, it jumped down to the next line. And that's what we know about program flow. It just goes down to the next line unless there's a condition or a loop in the way. So no stroke gets run. I asked it to step again, fill gets run, I ask it to step again, the next line's being run. But when I ask it to step again, I think it's going to do something. Yep. When I asked it to step again here, it didn't go down to line 15 because calling a function means executing its body. And so it has to jump down to the body to do the execution. And look what happened as soon as it jumped down to the body. 2 more variables came into existence. They were declared and their values were filled in. Their values were filled into 0 because that's where everything is on this first time around. And then when I step again, I'm going to step to the second line of that function and another new variable came into existence. Well, that's because I did the declaration there. And then when I step again, it goes back to that original spot because it's got to finish running that line. And that line's got a few more things to do. And notice that when it jumped back, those variables from and towards that we declared as secret private inside the function just disappeared because they've done their job now. They're not needed anymore. Then we'll finish up this line. So because there's 2 things to do on this line now. There's the call the function, which is what we just did, and then there's the variable assignment. So it'll do that for me. I don't think the numbers change though. And it steps to the next line. Guess what's going to happen when we step from here? Surprise, surprise, we're going to jump down to line 20. Bam. And again, from and towards come back into existence again. They were wiped out at the end of the last call. Now they're back again because we're back into the call again. And that's one of the cool things about functions. These variables that we declare on line 19 in the parameter list, they go away and come back every time the function gets called. They're kind of cleaned out, freshened up. So we jump back, we finish, we draw the ellipse, we finish. And draw is done and something happened. Don't think I can make my mouse appear anywhere else, but I'll try. And we're back up to the top of draw again because that's what processing tells us it's going to do. And I step top to bottom again. Oh, look at that. I got the X position to be something other than mouse X is now 27. So this time when we jumped into the function, the from and towards got declared, which means they came into existence. And the from got 0 because that's where it was before. But the towards got 27 because that's what was in mouse X. Int towards equals mouse X was what actually just happened when we jumped in. And because mouse X was 27, int towards equal to 27. And then we run this line, and look, ret's going to come up with an interesting number, 1, kind of interesting. And back we go. And then back in for ypos, and ypos got 34. So again, the variables came brand new into existence. Luckily, we cleared out the old ones. We didn't want 27 anymore. Cleared out the old ones, created them again. From got set to 0, because that's what ypos was. Towards got set to 34, because that's what mouse y was. So it was just like saying int towards equals 34. And then we run the body. Running the body creates the ret, which again is just 1. And we're done. Ypos is updated because we've done the second part of line 14. So ypos is updated, but we haven't done the second part of line 15 yet. But now we have. So ypos is updated, and then jam, that draw loops over, and it bounces back around to the next draw loop. Okay, so I was using the word draw loop there as well. Apologies. I try and say draw algorithm as much as possible. But because the draw function gets called over and over again, the draw algorithm gets called over and over again, just like a loop, we often fall in the habit of calling it the draw loop. Okay, so that's covered all the topics I want to talk about here. A reminder, of course, that this is just an addendum to the stuff that's already here. I don't need to go over the function basics and the modularity and the reusability the same way Daniel does. It's there. This is an alternate view on it. So we kind of went a bit round from the other direction, which hopefully is useful to some people who just find that way of learning more useful. But I will point out something else now, actually, that I just thought of, which is that this code is better than the code I had before in a couple of ways. It's better because this makes more sense. Line 14, before I made this change, was, just to remind you, it was, I've got to get it right, mouse x minus x pos divided by 24 plus x xpos. And that was correct, but maybe you were looking at it when I first wrote it going, what the heck why is that the right answer? And you should, because a little calculation like that is not entirely obvious. But now it should read much easier, because it just says, get a bit closer from xpos to the mouse x. That's more readable. We've added a little bit of documentation to our program. So the names of functions can be really useful to help you organize your program in a way that makes it readable. Another advantage is if I decided I wanted to go back to that moving a bit faster, I can just change it in one spot. When I was doing that experiment before, oops, the debugger's still on. When I was doing that experiment before, I was having to change it twice to make the circle move faster. Now I've got a single spot, or slower. I've got a single spot where I can change it to make it move slower or faster towards the, and it won't get within 80 or pixels or whatever because of the way modular arithmetic works. Just one place that I can change it, and that's actually another win. So we've got 2 wins here just from doing this little experiment. Better naming, which gave us a better, more readable code, and better modularization, which meant one place. The calculation was just only one place instead of 2, so I only had one place to change it. I've only got one place to have a bug. I've only got one place to fix any bugs as well. I also think that this line here, towards minus from plus from, makes more sense than mouse x minus xpos plus xpos, because, again, we've introduced some names for things that are more meaningful names than what the names were before. And since no questions have come through, I'll just finish up by showing you a change we could make to this to make it a little bit better. There is no need to store this variable on line 20 and then return it. Processing lets us do all of that in one step if we want. We can calculate a number. Just remembered one more thing to say. We can calculate a number and return it straight away. The reason I didn't do that is because it makes a one-line function, which is a little bit harder to trace. If you do the debugger, it just goes there and bounces back. But that works perfectly well too. So the other thing I wanted to remind you of was the difference between expressions and values. Sorry, expressions and statements. Every line of a processing program is a statement, right? Statement, statement. Well, not quite. A variable declaration from top to bottom is a statement, kind of. So this variable declaration from top to bottom is a statement, kind of. This one's a top to bottom statement. Function uses are expressions when they have a return type, and they are statements when they don't. Cool? This is where it gets a bit interesting. They kind of sit in between. Here's an example of a function call being used as a statement, because it's just on a line by itself, right? And here's an example of a function call being used as an expression, because it's giving back a value that we're then putting into a variable. It all depends. Because a function call does execute code for us, it does do a thing, then it's definitely in the category of statements. But also, if it does return something, as long as there's not a void in that return slot, then it can act as an expression too. And just to prove to you that it can act as an expression and a statement, if I get rid of this, processing doesn't complain. It's perfectly happy letting me use that variable there, use that function there as a statement. What happens to the return value? It just disappears into nowhere. Nobody gets to capture it. And we've broken the program a little bit. But I wanted to point out there that a function call is an expression because it returns something most of the time, but it could also be a variable. It can also be a statement if you want it to be. And if it doesn't return anything, then you're probably using it like a statement all the time. Okie dokies. That was the last thing I wanted to talk about. If we don't have any more questions, then I can finish up, but I'll just sit here quietly for a minute or two to see if any other questions come through. Quiet day today. Hope everybody's settling into their new world. I'm starting to settle into mine. I just live in this corner of my house now. It's not too bad. I can see outside. Okay, well, it was fun, and I'll see you next time.